Hello, this is Mr. McMurray, and welcome to Chapter 5, talking about momentum. All right. And if you remember, there's a while back we said you could have a semi truck sitting on the side of the road and a semi truck coming 65 miles an hour. And we said which one has the most inertia? And the correct answer is they're the same because inertia only depends on mass, and both of those have the same mass. But we know it's not the same thing if both of them hit you, right? And we just logically know that. So, but it doesn't have to do with inertia. It has to do with what we're talking about today, which is momentum. Momentum is mass in action. So this is not only the mass matters, but also how fast it's going. Okay, or you can think of it as inertia in motion because inertia depends on the mass. All right. So if we were talking about bowling balls, for example, I have a 16 pounder and a 12 pounder over here, and if I were to throw these at equal speeds, would I pick one over the other? Assuming I could throw them equally hard. Okay. Generally, I would take the heavier one. Sorry, this one, the blue one. Okay, and the blue one, why? Because it's a 16 pounder. It has more mass. Okay, and therefore it is going to have more momentum because momentum is determined by the mass and the velocity. So if I throw these the same speed, okay, then they are going to have the same momentum. Now, on the other hand, somebody consider the smaller ball. It has less mass, but I may be able to throw it faster, okay, and have a higher velocity. So it is possible for these two balls to have the same momentum, okay. If the lighter ball with less mass were going faster, and if the ball with more mass was going slower, they could have equal momentums, and therefore are just as likely to rattle the pins around at the end of the game. So momentum depends on those two things. The more the mass, the more momentum it has. The more velocity, the more momentum it has. Okay, and so you can adjust those to get however much momentum you need. All right, but it depends on those two things, just mass and velocity. And going back to semi truck, obviously the semi truck's going to do a whole lot more damage that's going 65 miles an hour because it has momentum. Okay, not inertia, but it does have more momentum. All right. Now, momentum, since it has velocity in it, which has direction, is also going to be a vector quantity, which means it has a magnitude or an amount, but it also has a direction. Now, normally, we're just going to be talking most of the time of momentum. It's either a positive number, which means it's going forward, or a negative number, which means it's going backward. Okay, we're not going to say east or west or 273 degrees off of north or whatever. Okay, we're just going to say it's either positive, it's going forward, and negative is going backwards. Okay, all right. But it does have a direction then. All right, and so we're not really worrying about the direction so much as positive or negative. We can say that basically momentum is mass times speed. Okay, now the formula for it is P, which is the Latin word that originally they used was impetus. Okay, impetus means a push, or you need an impetus to get you going. That means you need a push to get going. Okay, and so that's why it is a P. Momentum obviously does not have a P at anywhere, but it is a vector quantity, and it's equal to mass times velocity. All right. Um, Now, the amount of momentum then depends on those two things. Both, if you have something with a lot of speed and a lot of mass, like a semi truck, then it's going to have a lot of momentum. Okay, if you have something fairly small, let's say a mosquito has a small mass and relatively slow speeds, usually as they're hovering around, buzzing in your ears, then they're going to have a very small amount of momentum. All right. Now, if the momentum changes, and that's what we want to talk about now, especially when things hit each other. But if something changes the momentum, what changes? Well, generally speaking, if we have a bowling ball rolling down the lane, if it changes its momentum, it's either going to have to change its mass or it's going to change its velocity. Now, most of the time, it's not going to all of a sudden gain mass or lose mass. Okay, you could have a truck going down the highway, I guess, and a bunch of bananas could fall in the back of the trunk thing and all of a sudden increase its mass. But most of the time, if its momentum changes, it will be because the velocity changes. Okay, and we know that the velocity changes or it accelerates, decelerates, speeds up, slows down, or changes direction, it's going to be because there was a force acting on it. Okay, so anytime there's a momentum change, it's usually a change in velocity, and that's caused by a net force or a change in some kind of force. Okay, now the greater the force, then the greater the acceleration, and therefore it's going to have a change in velocity, and therefore it's going to have more of a change in the momentum. Okay, that makes sense. Now, it also depends how long the force acts on it. Okay, for example, if I'm throwing this bowling ball, once I let go of it down the aisle, am I exerting a force on it? No. So the time that I exert the force is only when it's actually in my hand and I'm pushing it forward. Okay, to use a different example, say we're at a baseball game. All right. Technically, it's not baseball. This is a softball, but that's okay. All right, same principle. So the softball's coming in. The force is applied when the bat hits it. Okay. As soon as it comes off the bat, it's no longer applying a force on it. Okay. So there's two things that are going to affect the change in momentum and how much it accelerates. All right, in the opposite direction is how much force you hit it with and how long the bat is in contact with the ball. Because once it's not in contact with it anymore, same thing if I'm throwing a pass down Weatherford College football. All right, and I'm throwing a pass down the field. Okay, it's not how long the pass is; it's the time that I'm actually pushing the ball. Once it leaves my hand and goes off, then I'm not putting any force in it. So it's the length of time that I apply the force to the ball. So when I'm actually touching it. Okay, now going back to the softball or baseball, when it comes in, one of the things the coaches will always tell you when you swing your bat is to follow through. Why do you follow through? Because if you just kind of hit it and stop, you're going to have a fairly short time that the force is applied, and therefore it's not going to go all that hard or all that fast the other direction. So you want to follow through so that you can hit it as long as you can. Okay, and someone says, well, that doesn't matter. But say it's 3/10 of a second instead of 1/10 of a second. Well, that's 3 times as long, which means it's going to influence the acceleration 3 times as much as if you only do it for 1/10 of a second. But we're talking about very small amounts here. But that's the same thing true with tennis, golf, swings, whatever. You want to increase, sure, if you can hit it harder, that's good, but the more force, but also if you can apply the force for the longest time possible, then you're also going to get a greater acceleration and get the ball to go farther. All right. So what we call that is the impulse. Okay. The impulse is equal to force times time. It talks about that in the other lecture, so I'm not going to go into that a lot. But the impulse is what we put on it to change the acceleration, change the momentum. We apply the impulse to do it. And it has to do with how much force do we put on it and how much of a net force and how long do we put it on there? For what length of time do we apply it? Okay, and if we increase both of those, then we have a greater impulse. If we decrease those, then we have a less of an impulse. Okay, now it turns out that if you put the formulas equal, and I think I did this in the lecture, you get where force times time, or the change in time, which is the impulse, is equal to the change in the momentum, which is the change in the mass times velocity, which is usually, like we said, a change in velocity. So basically what we're saying is the impulse is equal to the change in momentum. Okay, and so this is fairly important. Okay, say we have a ball that's moving at a certain speed. It's going to take a certain amount of force acting on the ball for a certain length of time to stop it. Okay, but if we change the amount of force, the amount of time involved, we can make some important differences. Okay, so let's talk about how impulse and momentum changes affect each other. Okay, all right, first one, if you increase the momentum by applying more force, obviously if you get stronger and you can swing harder and you can hit the bat harder on the ball, then obviously you can increase the force, and that's going to make it go farther and accelerate more, have a greater momentum change. It's coming this direction, so let's just say that's a positive. Now it's going to go back the other direction, so that would be a negative. But that's going to be a big momentum change. Okay, so if we increase the amount of force, then that's going to increase the momentum change. It's going to increase the impulse, which will increase the change in the momentum. All right. What if we hit it for a longer period of time? Well, we talked about that already. If we can hit this ball for a longer period of time before we let go of it, then it is also going to have a larger impulse and therefore a greater change in momentum. So if we can increase the force, that's going to increase the momentum change. If we increase the time, that's going to increase the momentum change. If we can do both, if we want to hit the ball as hard as we can, we need to get stronger so we can hit it with more force, but also follow through so we can hit it for longer time. And that way we get the maximum change in momentum. Okay? Yeah, so it has with time. All right? Now, this is also some things, we won't talk about this a lot because it's another one, but think about a pistol versus a gun, a rifle. When you shoot a gun, it explodes, gunpowder, and then you have these expanding gases that push the bullet out of the gun. All right? But once you get to the end of the barrel, a lot of the gases go off to the side, and for the most part, it's no longer applying a force. Now, if you have a pistol, which only has a short barrel, then it's only applying that force for a short period of time. And so pistols are usually for short range. See in the old westerns, they pull out their gun and shoot someone way up on the canyon wall. Ain't gonna happen, okay? 9 times out of 10. Well, 9 out of 100. Let's say just get really lucky, okay? Because pistols only have a short time of impulse, and therefore they don't have a lot of change in momentum, and you don't get an acceleration. A rifle, on the other hand, may have 2-3 feet of barrel, where that force is applied for a much longer period of time. So you get a greater acceleration, and you can shoot half a mile or a mile, depending on the rifle. Sharp buffalo gun is the one that we talked about. They can go really, really far. Okay, but it's because you're having a longer time of impulse, so you have a greater acceleration, and the bullet goes much, much faster, which means that you can shoot farther without it dropping as much. And that gets into gravity, which we'll talk about later, but you get the idea. Okay, with a rifle, you have a long time of the force applied. A pistol, you only have a short time. Okay, so obviously, if you increase the time of the force is applied or the amount of force, that's going to increase it. However, what's not so obvious is if you increase the time of the impulse, you can reduce the force. Okay, now, I cannot find the video. I will find the video. I will post it, okay? But where the video, but let me describe what's going to happen in this video, and then we will go from there, okay? I can't actually show you the video of it, and I can't do it with one person because I can't hold all the stuff, okay? But we will do it, okay? All right, let me pause for a second and get that. All right, here we are, and we're going to try to show you this as well as I can, okay? First of all, this is eggs. This would be an egg toss, okay? Now, if I take this egg, someone says, well, how do I know that you're not just giving me boiled eggs? How do I know if these are really raw and therefore dangerous? Okay, well, here's the deal. All right, let's say I take this egg and I spin it. It doesn't spin very good. That tells me that it is a raw egg. Now, if I keep spinning it, eventually I can get it to spin pretty fast, but initially it does not want to, okay? And the other egg, also just to demonstrate that I'm not swapping out with a boiled egg, same thing. You try to spin it at first, it doesn't want to do it. Try to spin it the other way, it's even worse. Okay, but eventually if you keep spinning it, you can get it to spin. If it were a boiled egg, it would spin good the very first time. Someone says, well, what's the difference? Well, it has to do with inertia. The inside of the egg is a liquid, and it wants more or less liquid, and it wants to stay still. Inertia. When I put a force on the shell, I'm not putting a force on the inside. The inside is trying to stay still, and the shell is trying to turn, and so it's very sluggish and kind of does that. Now, eventually, if I keep spinning it, I overcome the inertia of the liquid, and the egg starts to spin. However, if it's been boiled, it's all solid. When I spin the egg, everything inside goes with it, and it immediately begins to spin well. All right. Now, what we're trying to do here, like I said, I'll try to get the video posted, but I cannot find it right now. But if I take this sheet up and I hold it, and I have a little part down here that catches the egg, I can hold it up, and I can have people throw an egg as hard as they want to against this, and it will not break. We've had a student one time who eventually went to the minor leagues and almost went to didn't turn pro, but it got in the minor leagues, and he threw as hard as he could, still couldn't do it. Okay? Doesn't matter. If it's you, it's him, whatever, it will not happen. Someone says, well, how do we know this? Well, by physics, okay? And in this case, it has to do with momentum, okay? If I throw the egg, there's a certain amount of impulse that it will take to stop it, okay? If I throw it against the wall, it takes a certain amount of impulse and it will stop it. If I throw it against this, it will stop it. And it takes the same amount of impulse either way. But if I do it against this, I cannot make it break. If I throw it against the wall or this cabinet or any other solid object, it will break in a hurry and make a big mess, but I'm not going to do that because I don't have to clean it up. Okay, so someone says, well, what's the difference? Well, impulse has two things in it. It has force and it has time. And it takes the same amount of impulse to stop the egg. The total has to be the same. But when it hits the wall, the time is very, very small. So in order to make it the same amount of impulse, you have to have a big force. So when it hits a solid object, the time of the impulse is very small. That means the force is very big. Okay? Now, when it hits the sheet, okay, first of all, we talked about third law. For every, you can only exert as much force on the blanket as it exerts back. Okay? But in terms of momentum, what's happening is this. When it hits, it gives a little bit, and it still stops it. So you have the same total impulse as you do when it hits the wall, but the time is longer because it hits it and goes back in and stops. Okay? And so it takes, say, 3 or 4 tenths of a second instead of a tenth of a second. Once again, that means the force is only be 1/4 or 1/5 as much, and it's enough that it will not break the egg. Okay, so impulse has two parts, and if you do it over, if the impulse is spread over a short period of time, you experience a big force. If you spread it out over a long period of time, then you only need a small amount of force. Okay, and so that's the difference between the two. And like I said, I will try to get that video for you of us going outside and doing that. Okay, but I don't know where it is right at the moment. Apparently, it's not in the file where it's supposed to be. Okay, but basically that's it. So it depends. If you're doing a karate chop, for example, they hit it. But not only do they hit it, but you also kind of notice they kind of pull their hand up after they want to deliver the maximum amount of force. It takes a lot of practice to do that, and they have to toughen up their hands and stuff so they don't, break them or stuff like I would if I did it. And then they also pull it back up, so the time of impulse is very small, which increases the force of the impulse. Okay, and so it puts more force on it. Now, once it puts that force on the board or the brick or cinder block, whatever it is, then that sends vibrations through it, which the wood and the cinder block cannot handle, and it starts breaking and cracking, and it shatters it. Okay, you notice they don't do karate chops to solid steel bars. Why? Because they will not do the vibration thing, and they will not have enough force to break it. That would break their hand. Okay, but if they do it with certain materials such as wood blocks and cinder blocks, then they can put a short enough impulse with enough force that it will break it and cause it to shatter, which is impressive, I think. Now, another thing about momentum changes, okay, has to do with bouncing. Okay, for example, we have two black balls here. We drop these balls, one of them bounces just like that, and one of them does not. Okay, these are called happy sad balls. Okay, I technically give you one and say, hey, I bet you can't bounce as high as I can, and you'd lose because it's just the way the ball is. It does not bounce. It's just, they look very similar. They're made out of similar types of rubbers, but they're not the same. So one of them is very bouncy, one of them does not. Now, okay, so what? But the momentum change is not the same. Okay, this one, which I believe is the no bouncy ball, yeah, that's the bouncy ball. All right, this is the no bouncy ball. All right, now if we take the no bouncy ball and the bouncy ball and put them back the same amount, let me experiment a little bit here. We're going to let them hit these blocks of wood. Now these blocks of wood are exactly the same size, shape. They're interchangeable. I can put one back there. It's going to look the same either way. Trust me on this. But okay, so if I take these back a little bit and I let them hit it, turns out this one falls over, this one does not. They were back the same distance. They hit things that they should have delivered the same momentum, right? Okay, but here's the difference. Okay, when the bouncy ball hits this, all right, think about it in terms of force, Newton's third law. First of all, it delivers a force on the board, and the board delivers a force on it. Then when it bounces off, the board delivers another force on it, and it delivers another force. So there's two action reactions, one when it hits and then two when it bounces off. So you get double the force, okay? And so that's why the bouncy ball made the block turned over, but the other one did not. The other one hits it and then just stops. And since it doesn't push back off again and exert another action reaction, you don't get as much force applied, okay? And so the bouncy one has a greater change in momentum. Now that's in terms of impulse, because it's a greater force, because there's a force when it hits it and the force when it pushes back off of it. And there's action reaction both times, force acting on the block and acting on the ball. So it's getting a double dose of force. So in terms of impulse, it's getting a greater impulse, because in the same amount of time, this one just hits once and it applies a force. The bouncy ball is hitting and applying a force twice. It hits it and then it pushes back off from it. So it gets two forces applied to it, because they're action reaction, and as well does the block. The block falls over and this one bounces back more. Now, in terms of momentum, which is mass times change in velocity, momentum change is mass times a change in velocity. Okay, well the mass stays the same no matter what, but the velocity, say they were both coming at 2 meters per second, okay, and they hit the board, okay, that means this one went from 2 meters to 0 meters per second because it stopped, okay, so negative 2 meters per second would be its momentum. But this one hit it, went from 0 to 2 to 0, but then it came back this direction, let's just say at 1 meter per second. So it had a total change of 3 meters per second, because it was 2 this way, and then it's going back the other way, another one. So that's actually a change of 3 meters per second. So there's a bigger change in velocity for the bouncy ball, because not only does it come down to 0, slows down to 0, decelerates, but it actually decelerates and goes back in the other direction even more. So you have a greater change in velocity. So either way you look at it, from action reaction, the force is greater, so there's greater force of impulse, and that's why bouncy things have more. But also that is why, from terms of a change in velocity, a change in momentum, which is mass times change in velocity, you have a bigger change in velocity, because not only does it stop when it hits it, but it also accelerates back in the opposite direction, okay, which makes it an even greater change in velocity. This is one I came up with myself. I have little sticky darts here, okay, and if I throw them at something, they will stick, okay, and you may have seen it move just a little bit when it hit there, okay. So if I throw that one as hard as I can, and it kind of moves. All right, now this one has a rubber ball on the end, so it makes it bouncy. So not only is it going to hit and stop like that one did, it's going to hit and bounce back off. Notice, throwing it about the same speed, it knocked this over, which did a chain reaction, but that's a whole different thing. But yeah, it hit this one and was actually enough to knock it over. What's the difference? Not because of, they both had about the same velocity. That one had it bounces. This one, on the other hand, hits it and knocks it over. Why? Because this one bounces. So it applies a force when it hits on the block and the block on it. And when it bounces back off, it applies a force on the block and the block applies a force on it. Okay, so it gets double the force of impulse. It also has a greater change of velocity. Not only does it stop, but it actually bounces back to the other direction, so it has a bigger change, okay, in the velocity. All right, now another thing is, in a closed system, which just means there's no outside things affecting it, the amount of momentum in the system is conserved. Okay, for example, if I had a cue ball, it hits all the other balls and scatters them off, there's still the same amount of momentum after it hits the cue balls then the cue ball hits all the other balls as there was from the cue ball. Now, that means the cue ball was coming in with a lot of speed and the mass of one ball. Once it hits those 10 balls, now that momentum and the speed, velocity has to be spread between those other balls so that it equals the same amount of momentum. That means momentum is conserved. As long as we don't reach over and hit the balls or something like that, that will be true. Okay, now in this case, we're going to have a ball here. We're going to drop it. This is going to hit it. This one has a little gap there, and it will hit this ball. All right, it'll pass its mass, its momentum to this ball, which has a smaller mass. In order for it to have the same amount of momentum, what has to be true? Think about that. Then this one's going to hit a smaller ball, which has less mass. So if it's still going to conserve the momentum, what has to be true? And finally, it's going to hit this little one on top, which can actually come off. Okay, and let's see how this works. Sometimes it takes a couple times. I have a hard time dropping it straight. All right, here we go. All right. Still bouncing over here, but I don't know if you can see that one. That one hit the roof. The top one hit the roof, and it went fast. Okay. Now, someone said, "Well, what happened here?" Okay. Well, like we said, the momentum is conserved from when the first ball hit. It had a big mass and whatever velocity when it hit the ground. It passed its momentum to the smaller ball, the next ball up, which is smaller, has less mass. For it to have the same momentum, which is mass times velocity, it has to have a lot higher velocity. And it passes its momentum to the next ball, which is even smaller. So if it has a smaller mass, the only way it could have the same momentum is if it had even more velocity. And finally, it hits the little red one on the top, which in order for it to go flying off, it has even less mass, so it has to have even more velocity. And so it shoots up, hits the roof, and bounces back down so quick you may or may not be able to see it on this camera. All right. So that we've taken this one out in the gym sometimes, and it never hit the top of the gym, but it gets pretty high up there sometimes. Okay. A simpler thing is this doohickey. All right. It would have a straw with a bouncy ball stuck on the end, very sophisticated. And this one we have a bigger straw that will fit over that one, so it fits on top of it. It has a little foam thing at the bottom here so that it will hit the ball down here, and then it has a little brim up here just to give it a little weight so it doesn't go flying off to the side or something like that. Okay, now let's check their masses real quick, and then we'll be right back. All right, so if we take this first one, the ball with the straw and the bouncy thing, it has a mass of, hang on, just went off, hang on. All right, you know how it is, technology. Okay, so I put that on there, and it has about 8 grams, okay, 7.9 to 8 grams. The other one I put on there only has about 1.2, so this one has almost 8 times as much mass. All right, and if we drop it, it will bounce back up to my hand, okay, pretty good. Let's see what happens when we put it on top of each other. And now I drop the first one. All right, so we drop this one, which has about 8 times as much mass, okay? Now, when it, or 7 to 8 times, when it hits this one, it transfers its momentum to this one, which only weighs about 1/8 as much. And so this one is going to speed up, okay? And so it's going to speed up a lot faster and go a lot higher up in the air. Once again, the idea of conservation of mass, okay? And so if a heavy object hits a lighter object, then it's going to cause the lighter object to have to go faster if it completely absorbs its momentum, okay? So the amount of total momentum still has to stay the same, and therefore the only way it can do that is for the smaller item to go faster. Now, in your book, it talks about, in the lecture, I'll go real quick, if you have a cannon shooting a cannonball, okay, we know the force acting on each of them is the same. We know they act for the same length of time, which means that you have the same impulse on the cannon and the cannonball, okay? But even though you have the same amount of force for the same amount of time, that has to be equal to their change in momentum, which is their mass times the change in velocity. Well, the masses are not the same. The cannon has a really big mass, so it has a very small change in velocity. It kind of goes back a little bit. The cannonball has a small mass, but has a big change in velocity, and it goes shooting out and hopefully smashing into the other people's fort, ship, whatever we have to be shooting at, okay? And so keep in mind, even though the change in momentum is the same, the effects may be greatly different if they have different masses, okay? And so if something has a small mass, something else has a large mass, well, the large mass is going to have a small change in velocity, and the small object, the cannonball in this example, is going to have a large change in velocity. And when you multiply the small mass times the big change in velocity and the big mass times the small change in velocity, you're going to get the same change in momentum. Okay? All right. Now, when we talked about the example of a mosquito running into a semi-truck, okay? Say the truck is going 60 miles an hour. Let's say the mosquito is going, I'll give it a mile an hour just to give it a benefit of a doubt, probably not going that fast, but yeah, and they hit, okay? Now, let's think about what is the same and what is not the same. Which one exerts more force on each other? Well, according to Newton's third law, equal and opposite action-reaction force. So the force that the mosquito puts on the windshield and the windshield the truck puts on the mosquito are the same. The length of time is the same, okay? So the impulse is exactly the same. The change in momentum, then, we know impulse is equal to change in momentum, so that has to be the same, okay? Because the mosquito, which was going 1 mile per hour this direction, now is going 60 miles an hour the other direction, or pretty close to 60 miles an hour the direction, the opposite direction. It had a big change in velocity, okay? But it has a small mass. The truck has a big mass, but it has a very small change in velocity. It just looks like it's still going 60. You probably couldn't even, 59.9999999, whatever. It basically doesn't slow down hardly. All right, so they would still have the same change in momentum, okay? Because one of them has a big mass, small change in velocity. The other has a tiny mass, but it has a big change in velocity. And so their change in velocity would be the same. The impulse would be the same. The force that they feel is the same, because Newton's third law says for every now, what is different is the acceleration or the change in their motion. That is not the same. The truck basically doesn't change at all, and the truck does, the mosquito does a whole bunch. Okay, so keep that in mind. If the force is the same, the time is the same, the impulse is the same, and that means the change in momentum is the same. Okay, but that does not mean the change in velocity or the acceleration is the same, and that's what's different depending on the mass of the two objects. Okay. So let's start talking about collisions, which is kind of what we've been talking about really with all these things. They're different collisions, okay? There are basically two kinds of collisions. There are collisions where two objects hit and stick together, and there are when they hit and bounce off, like two pool balls would do, okay? Basically, if they are elastic, they snap back. Okay, remember elastic, if you have underwear, it's elastic. It doesn't mean that it stretches. Even old underwear that no longer fits anymore, been worn out, it still stretches. The problem is it doesn't snap back like it's supposed to be and fit tight. So elastic means it snaps back, so that means they hit, but then they also snap back and go apart from each other. So if they're elastic, is when two objects hit each other and then they bounce back apart. Inelastic is when they hit together and they get tangled together and become one object and act as one object. Now, if you think about car accidents, there are some that are, there's all the ways in between. You have completely inelastic, where they just become one big molten mass together, and so they move together after that. And there's other ones where they hit and then they bounce off of each other, and so they're kind of elastic. They can be both. Most collisions are somewhere between. They're mostly elastic or mostly inelastic. Okay. The only time they're perfectly elastic, that things just really bounce off perfectly, is in microscopic atoms, on the atom level, atomic level. Individual atoms, because they are surrounded by electrons that have negative charges, they actually never touch each other. They hit and bounce off, but they never actually touch because their charges repel each other. Just like you have two magnets with the same charge, north pole, you try to push them together and they just repel each other. Okay, then that would be an example kind of what we're talking about here. Okay, so let's talk about some collisions and what happens and how they're different in each other, and let's use our air track to demonstrate this. Okay, now, first of all, let me find my little slider things, and then we'll be ready to go. All right, here we go. We've got our setup here. I think where you can see it. All right, this is our track again. We have two things here. So what I'm going to do first of all, we're going to do this one. This one has a spring on the end, so it's going to hit it, and it's going to be an elastic, pretty close to a perfectly elastic collision as we can get. So we're going to do that first. Now, as you may have noticed, when this one came in, it had a certain mass and a certain speed. Okay, this one has the same mass but no speed, so it has zero momentum. This one has, let's just say, a speed of 1 meter per second and 100 grams, so it's 100. Okay, when it hits this one, then you notice this one went off at the same speed as that one had been. Okay, and so it has the same mass, same speed, so it has the same momentum this one did, and now this one has a momentum of 0. Okay, all right, so it's still the same amount. This one had all the momentum before, now that one has a momentum, but it's the same amount since they have the same mass and they were moving the same speed. Okay, and that's an elastic collision. That's what has to happen. Now, momentum being conserved means you have to have the same before and after. All right. Now, what if they had been coming toward each other? Let's try that real quick. What if they've both been coming toward each other at the same speed? What would their momentum be? Let's try. All right. Now, the way that one works, you notice, they came together. Now, this one had, let's say, 100 units of momentum that direction. This one had 100 momentum this direction. Since they're in opposite directions, one of them, we're just going to pick this one and say it was negative. So this is 100 positive, 100 negative. Their momentum is 0. 100 minus plus a negative 100 is 0. So the total momentum was 0 to begin with. Now, after they hit each other, they both went the opposite direction. Once again, this one went that direction, it had a positive 100. This one went the opposite direction, it had a negative 100. 100 plus a negative 100 equals 0. So the momentum was the same, even though they both ended up going in different directions. Okay, they ended up going at the same speed in opposite directions. And so basically, because one's going in opposite directions, the momentum is 0. Okay, this is just like a cannonball. Before you shoot the cannonball off, the momentum of the cannon and the balls go 0. So they start off with 0. Afterwards, you have the cannonball going off one direction very fast, small mass, and you have big mass, but they're going in opposite directions. So one of them's a negative number, and they cancel each other off, and it still has a net momentum, if you will, of 0. Okay, so momentum is conserved. Now, let's look at what if we had an inelastic collision. All right, this one I've got some with Velcro, so they'll stick to each other. So let's see what happens. First, I'll start with this one not moving anywhere, and this one coming into it. All right, what you should notice is that once they stuck together, this one had, let's say, 100 units of momentum going in, okay? 100 grams and then a speed of 1 meter per second. Okay, once they hit, now they're stuck together. They have a mass of 200, twice as much mass, but you will notice they go at half the speed. So the total amount of momentum stays the same in the same direction, still going this direction. Now you have 200 grams, but only going half a meter per second, half as fast, and you still have 100 units of momentum. Okay? All right. So let's try one last thing. What if they're both moving toward each other and then they stick to each other? So you notice this time, once they hit, they pretty much stopped. Okay, a little bit. That probably didn't hit them exactly the same speed, but they basically stopped. Okay, and this is kind of like the reverse of the cannonball thing. This one had 100 units of momentum this way. This one had 100 units this way. When they hit, they stop, which means their momentum is velocity 0, so their momentum is 0, and so they still have a total of 0. Originally, it was 100 this direction, 100 this direction. One's negative, so they cancel each other out, and once they hit, they stop. Okay, so that's just kind of a difference in elastic versus inelastic collisions. Okay. But either way, doesn't matter. Any kind of collision, elastic or inelastic, doesn't matter what kind, momentum is always conserved. All right. Have a great week, and don't forget to do your questions and be ready for your quiz. Have a great week.